All right, so in this chapter, we'll do DC circuits. This is direct current circuits, okay? Circuits where the power source is a DC voltage, okay? So let me motivate this chapter. Okay, so nowadays you guys are used to very powerful devices, handheld devices. Okay, this is an integrated circuit which has, I don't know, probably millions of elements in it. Okay. So here's something that you guys all walk around with. Okay, what does this device do? You guys know what does this device do?
Power the earbud speakers.
Okay, it's an amplifier. Okay, so your phone sends you a signal, an electrical signal, which contains audio information. Okay, and by the time it gets to the earbud, this little device here, that is the amplifier. That's all this circuit. Okay. And what does this do? Okay, so the signal that is coming in there into the audio is that. Okay, so that's the voltage that is coming as a function of time. Voltage as a function of time. And if you feed this to the microphone, that won't sound loud enough. So what you have to do is, you have to take this signal and increase the amplitude. That's what an amplifier does. Okay, so what you have to do is, you have to not distort the signal, but amplify it. Okay, and that's the job of this guy. All right, well, this signal is small. This signal contains more energy. So how did they do this? You have to pump energy in. So here's the battery, which is in the phone. So you're using the phone's battery itself to amplify it. And the reason this is outside is you could have put it in the phone itself. It would just make the phone bulkier. Okay. All right, so here's an amplifier signal, circuit. Okay. Now each little device has a function. This is a transistor, this is a capacitor, resistor, and so on. This is a diode, and so on. Each of those elements have their own function. Okay. Again, your goal is to amplify the signal without distorting it. Okay. Now, when you analyze a circuit like this, what you'll need to know is what is the current flowing through each element. Okay. And that is called solving a circuit. Okay. Finding out how much current flows through each element. That tells you how bright each element glows, so to speak. Okay. So if it's supposed to make your toast, how fast will it make your toast? And so on. Okay. So the general goal of this chapter is you'll have we won't do anything this complicated, but your ultimate goal is you'll have a complicated circuit with many elements, and solving the circuit will mean what is the current through each element. Yeah, so that's your goal. All right, so now let's start off with some basics. So here's a battery. This is what is called a load. A load, here it's represented by a resistor. It could be a light bulb, it could be a toaster, it could be a washing machine or whatever. Okay? A DC motor. Okay, so here's the battery. In a battery with metal wires, what really happens is electrons move from here and go through the load and go there. Okay. Now this convention for currents was adopted before we knew about electrons. So back then they thought that some kind of positive charge was moving from here and then going around like that. Okay. So we'll stick with that convention. Now, you guys remember from last time, the potential energy is the charge times the potential, electric potential. Okay, this is potential energy, this is the charge, this is the electric potential. Okay, so let's say we place a positive charge here, that is at a higher voltage, and that's higher potential energy. Okay, so what the battery supplies is a positive charge at a high potential energy. And when this charge goes through the load, that is when the current flows through the load, what it does is it gives up its potential energy. And this device converts that energy into whatever it is that you want to convert. If this is a light bulb, what did you do with that potential energy? I'm sorry?
Light?
Yeah, converted that to light. If this was a toaster, you converted that to heat. If this was a washing machine, you converted that to mechanical energy. If that was a car, you converted that to mechanical energy. Okay. Anyway, so here was this charge that had potential energy that got converted to whatever it was that converted, and now the charge has lost all its energy. Okay, and it's come back to the battery. It's come back home. Now, what does the battery do?
Pushes it back up again.
How does it do that?
Chemical energy.
Yep, so the battery now will use some of its chemical energy and lift this back up to the hill. And that guy goes around and spends it right away. So that's the cycle. Okay. How long can this thing go on?
The battery runs out.
Oh, well, runs out of what?
Physical energy.
There you go. All right. So that's the deal. All right. Now what this is showing you is, again, here's the battery. There's the negative terminal. There's the positive terminal. What this is the internal resistance of the battery. Okay. And here's the external load. Okay. Now, you see, so what this is the EMF of the battery. That is the maximum voltage the battery could provide. Okay. Now, if you connect a load, what you do is so when the current flows through here, there's a voltage drop across the internal resistance, and here's the external terminals of the battery. So what you see, the voltage you see, is less than the maximum voltage that can be provided, because there's a voltage drop across this internal resistance. Okay, so that's what this is saying. The terminal voltage, that is the voltage you see outside on the battery, is E, the EMF of the battery, minus the voltage drop across the internal resistance. Now, if the internal resistance was 0, then you would see the maximum voltage. Okay, so that's what that is. Also, you would see the maximum voltage if this load resistance is large compared to the internal resistance. Okay, if this is very large and this is negligible, then the current will be small, this term will be small, and the terminal voltage will be approximately equal to that. All right, what is a battery?
Container of chemical energy.
It's a store of energy. It's a packet of energy. Okay? And the battery supplies this energy to whatever needs that you need. All right, the power is the rate at which the battery is providing energy. Okay? What this formula says is, okay, so power is I times the EMF, the current flowing out of the battery times the EMF of the battery. Okay? So this is the rate at which the battery is providing energy. That is the rate at which it's converting chemical energy to electrical energy. I square R, this is the rate at which the energy is being supplied to the load. And the load might be doing whatever it's doing. So a light bulb is converting that to light, and so on and so forth. I square little r, that is the energy being dissipated in the internal resistance. That's being wasted. Okay? That's being converted to heat and all that kind of stuff. All right, so this is your useful power supply, and this is the energy wasted in the internal resistance. Okay, so here are two devices. These are the loads. These guys are connected in series to this battery. Okay, and so when loads are connected in series, their equivalent resistance is just the sum of the resistors. So when you connect resistors in series, you just add up the resistors. Okay, so if you want a larger resistance than you have, you just connect a bunch of them in series. Now the problem with this sort of connection is, do you guys see any problem with this kind of connection? Let's say there's 1,000 of these devices connected in series. One guy goes bad, everything shuts down. Okay, yep.
Like Christmas bulbs?
That's right, okay. So that used to happen all the time. But that doesn't happen anymore. What happened?
Connect them in parallel?
What's that?
Do they connect them in parallel now?
No, they still connect them in series. So now they invented something new. So when this dies, this element melts. Okay, so I'm going to draw a bigger picture. So this element melts, and as it's melting, what happens is these guys, this also heats up, they make it thin enough, and it joins. So the bulb has gone bad, but an electrical connection is maintained. Okay. All right, so okay, so you can do that for little devices and stuff like that. But in general, if you want to connect thousands of devices, you don't want to do that in series, because one thing goes bad, then So that tells you something. Okay. So this is the power company, and think of these as houses. All houses are connected in parallel, because if, let's say, one house burns down or whatever, something happens to one house, there's still power to the other houses. All the devices in your houses are connected in parallel. If your range breaks, that doesn't mean your TV won't work and all that kind of stuff. Okay? So when you have to connect a lot of different devices, you want to connect them in parallel. Okay, so in a series connection, the total resistance is just the sum of the resistors. Okay? Here's a parallel connection. Okay, so in this parallel connection, each of the devices is seeing the same voltage. Okay, and so here's a current going through this, here's a current going through that. Okay, now if this thing goes bad, that will still function. Okay, and this is the experiment we did this week, series and parallel connections. Okay, the equivalent resistance of a bunch of parallel connected resistors is the inverse sum. The equivalent resistance is 1 over R equivalent is equal to 1 over R1 plus 1 over R2 and so on. And it turns out that this resistor will be smaller than any of these guys. Okay, and you can see that. Yeah. So this number is this number plus and so on. So this number is bigger than any one of them. And since this number is bigger than any one of them, this number has to be smaller than any one of them. Okay? All right, so when you want something smaller than what you have, you connect them in parallel. Okay? Here's just a fun problem. I might buy you a soda if you want to try and solve it and get it right. Okay, so here's an infinite ladder. Think of them as all of 1 ohms. And find out what the value of this resistance is. Okay, so I'll give you a hint. Okay, so imagine this was not there. So this would have been 3 1 ohm resistors in series, so that would have been 3 ohms. But to this guy, there's something connected in parallel. So this is less than 1 ohm. So this resistance, R, has to be less than 3 and greater than 2. Okay? All right, try and think about that one. All right, so here is the punchline of the chapter. Okay, what you'll be interested in solving is, so here's a simple example of a circuit with multiple sources and multiple elements. Okay. Now, for example, this is if you have multiple sources like this, this is easy. So if this was each were 1.5 volts, 1.5 volts, 1.5 volts, when they're like this is effectively just 4.5 volts. This is just like a single source, and this is easy to solve. Okay. But of course, we are interested in more complicated stuff. So you can see that here's a source in this loop, and here's a source in a different loop. Okay. So here's a network circuit. Okay. And you want to be able to solve a circuit like this. And solving a circuit like this just means that finding a current through every arm. So this is an arm. This is a junction. A junction is a point where more than one arm meets. More than 2 arms meet. 1, 2, 3. Okay, so that's a junction. This is an arm. The same current flows through a given arm. Okay. So here's a current flowing through this arm. We'll call it I1, just like X, Y, and Z. Current flowing this arm we call I2. Current flowing through this arm we call I3. So those are the unknowns. Those are your X, Y, and Z. And solving a circuit just means solving for those 3 currents. Okay, so if you have 3 unknowns, how many equations do you need to solve them? 3 equations. Okay. So now we need some kind of law to come up with the equations to solve these circuits. And Mr. Kirchhoff gave us 2 rules to come up with these equations. Okay, so here are the Kirchhoff's rules, and this is the punchline of the chapter, like I said. Okay. What Mr. Kirchhoff says is, here's a junction. So the junction rule says the following, and these rules are very obvious. The current flowing into a junction is equal to the current flowing out of the junction, which makes sense. You know, current flows in, and you can't have charge collecting at any point in a circuit. So current flowing in should equal the current flowing out of the junction. So in this case, If you're looking at this junction, I3 is flowing in, and I1 and I2 are flowing out. So the junction rule would say I3 equal to I1 plus I2. And that's what this equation is. The current flowing into a junction is equal to the current flowing out of the junction, sum of the current flowing out of the junctions. All right, the second rule is the voltage rule. Now, before I tell you that, let's do an analogy. Let's say here's a mountain and you're going for a hike. Okay, you started here and you walked around there. You had an elevation change. Okay, let's say you climbed up 10 meters. And then on the next step, you descended 5 meters, and so on. Okay. And so when you have come back to your starting point, what is your elevation change, total elevation change? 0. Okay. All right, now keep that in mind. So in this, so now what we'll do is this is the voltage rule is also called a loop rule. Okay, here is a loop. At every point in the loop, there's a specific value of voltage. Okay, and so the voltage changes across electrical elements. Okay, so let's say this is at a low voltage, that's at a high voltage. You go across, the voltage change is positive. Then you go from a high voltage to low voltage, the voltage change is negative. Okay, so let's say if this point was at 10 volts, if you go around that loop and come back to the starting point, the sum of the voltage changes across each element, if you add them all up, that should be 0. That's the voltage rule. Okay, so that's what this loop rule says. The sum of the voltage changes across each element around a loop should add up to 0. Okay? So 2 very intuitive rules. And between these 2 rules, you can get as many equations as you want, as is needed to solve the problem. All right, by the way, so when you apply this voltage rule, the change in voltage across this element, so in this equation you'll have how many terms? The change in voltage across this element, voltage change across that, voltage change across this, voltage change across that. You'll have 4 terms. Okay, so when you go around the loop, the number of terms you will have in the equation is as many elements as there are in the loop. How many loops are there in this circuit? 2. 1, 2, 3. Okay, so the loop rule itself can give you 3 equations. And then you have the junction. How many junctions are there? There are 2 junctions, but since these 2 junctions are on the opposite ends of the same arm, they'll give you the same equation. Okay, so generally you just you apply one junction rule and then get the other 2 equations from loop rules. Okay, but anyway, you'll never lack for enough loops to get the necessary equations. Okay. All right, so we've said a lot, so let's back up a second. When we say we want to solve this circuit, what does that mean?
You want to find the current at all locations?
Yes, so you want to find the current through all elements of the circuit. That's what solving the circuit means. Okay? For this particular circuit, there are 3 arms and there are 3 unknown currents. And you would need 3 equations to solve it. So you use the junction rule and the loop rules to get the equations. Okay. Next week in lab, we'll set up a circuit like this. We'll calculate the currents, we'll solve for the currents, and then go measure it. Okay? So I might solve a problem like that. Actually, I might solve the exact same problem as we'll do in lab at the end of class. So we'll come to that. Okay? All right. Now we'll look at some sign conventions. Okay. So current flows from a higher voltage to lower voltage. So when you're going across this element, if you're going in the direction of the flow of current, then this is at a higher voltage and that's at a lower voltage. So change in voltage across that element is negative IR. Okay, this is at a lower voltage. VB is at a lower voltage. Okay, and the voltage drop across this is IR. So the change in voltage across that is minus IR. Good way to remember again the analogy to elevation. Water flows downhill. So if you're flowing with the current, okay, voltage is decreasing. If you're going against the current, okay, if you're going against the current, then you're going uphill and change in voltage is plus IR. If you're going from the negative terminal to the positive terminal of a battery, change in voltage is plus V. If you're going from positive to negative terminal, you're going from a higher voltage to lower voltage, change in voltage is negative V. Okay. All right. So again, in this circuit, there are three unknowns and you need three equations to solve them. And all right, so let's set up the three equations, for instance. Okay. So first one we'll set up is the current rule. The current rule says current flowing in is equal to current flowing out. So I3 equal to I1 plus I2. That's equation one. Okay. Now let's set up the loop rules. Okay, so we'll set up these. So what we'll do is we'll call this loop 1 and we'll call this loop 2. Okay, for loop 1, okay, we'll start off at this point and account for the voltage changes across each element. Okay. So when I go across this element, I'm going from lower to higher voltage. The change in voltage is plus E1. That's the EMF of the battery. And then the current is flowing this way. I'm going from higher voltage to lower voltage. The change in voltage across this element is minus I1 R1. Then across this element, minus, again, current going from higher to lower voltage, minus I1 capital R1. And then I go back along this way, minus I3 R3. And I've come back to my starting point, so all these terms should add up to 0. Okay. So there is the second equation. So in a problem, you'll be given this, you'll know all of these. The only unknowns are I's, the currents. Okay. Similarly, loop 2. Okay, so we'll start here. It doesn't matter where you start. Okay. So we'll, again, and it doesn't matter what direction you go. So let's say we'll go in this direction this time. Okay. So we'll start here, go in this direction. So now this time you're going against the current, so it's plus I3 R3. And then you're going in this direction. Okay, so when you go in this direction, you're going from lower to higher voltage. Okay, that's plus I2 R2. Then you're going in that direction from low to high voltage, that's plus E2. And then again, plus I2 R2. Okay, equal to 0. All right, let me ask you something. See, all the terms seem to be positive, and they're adding up to 0. See, E2 was positive. So what does that mean? I2 must be, one of the currents must be negative. What does a negative current mean? That in the real circuit, it's really flowing in the opposite direction. Okay, so that's what negative currents mean. All right, so again, so you set up equations, and now you have 3 equations and 3 unknowns, and you should be able to solve it. Okay. All right, I'll do an example in a little bit. Okay. All right, to summarize again, you'll have circuits with multiple sources. And what you want to do is, when you solve the circuit, you want to find the current through each element. And why do you want to find the current through each element?
Just solve the circuit.
I'm sorry?
Solve the circuit. Solve the current.
Right, that the current through each element tells you how bright the bulb glows. Okay? And that's what you want. All right, so now this is a basic RC circuit. And this is a circuit in your flash camera. This is your flash camera circuit. This is your pacemaker circuit, and so on. This circuit shows up in a whole bunch of places. Okay? So we'll learn to solve this, and it'll also teach you many other things. Okay? So here's a battery. Here's a capacitor. This is called a parallel. This is a parallel plate capacitor. Okay? But it can be any capacitor. Here's a resistor, and this is an electrical switch. All right, let me show you. Okay, here things will happen very fast. In fact, it'll happen in the blink of an eye. Okay, so what we're going to do is we're going to use a 1.5 volt battery. Okay, and what I'll do is I'll close the switch. What do you think will happen when I close the switch?
You'll charge the,
Yeah, it'll charge the capacitor. What will happen is electrons will flow from here to there. Electrons will collect here. Every electron that comes here will repel an electron, loosely speaking, and that electron will go over here and go to the battery. So in the end, this will become negatively charged, and that will become positively charged. Notice no charge is crossing this thing. These charges are repelling those charges. Yeah. So when you charge a capacitor, each conductor will have an equal charge. Okay? All this happens very fast. Okay? Okay, so there is the charge capacitor. What we are interested in learning is how does the capacitor charge? Okay? So that's what we want to learn. Okay? So here we go. All right, so here's the battery, here's the capacitor, resistor. Okay, what you learn soon is the bigger the resistor, the slower the capacitor charges. Okay, and so that's what happens in your flash camera. If you want let's say you're a professional photographer and you're taking a flash picture, and then you want to take another flash picture fast, that capacitor had better charge fast. But if you're charging fast, then the currents are higher, and then the risk of burning stuff is higher. Okay. Anyway, the larger the capacitor, the slower the capacitor will charge. All right, so here we go. Initially the capacitor is uncharged. Now we'll close the switch, and the capacitor starts charging. Okay. As the capacitor is charging, the charge in the capacitor is a function of time. Okay? And what is happening as the charge is building up? Oops. As the charge is building up, the current in this thing is dying down because the capacitor can take a maximum charge, and as the charge is building up, this is decreasing. Okay? And what is the current? The current is the rate at which the charge is building on the capacitor. IT, the current in the circuit, is the rate at which the charge is building in the capacitor. So those two are related. All right, so here is something, all this thing is happening within milliseconds, and we want to describe that. We want to understand that. Okay, so we want to understand the functional form of QT and IT. All right, so now you've learned the Kirchhoff's rule, so you can set up the equation governing the behavior of this circuit. Okay, so we will come up with a mathematical model to describe the behavior of this system. Okay, you close the switch, now you have a complete loop. Okay, and what did Mr. Kirchhoff tell you about the sum of voltages across all elements in a closed loop?
Or the changes, the change in voltage?
Yeah,
Equals 0.
the sum of those changes will be 0. So that equation will give you the mathematical model. All right, so let's start off here, and we'll go around like this. Okay, so when you go, see, this is at a lower voltage than that, so when you go across, the voltage across that increases. Okay, well, so the equation is set up going around like this. Okay, so we'll, here's the equation. I've set it up where I'm starting here and going around like that. I'm starting here and going around the loop like this. Okay, so the first element I go across is the battery, and you're going from low to high voltage, so that's plus E. And then I'm going across the capacitor. You guys will remember for the capacitance, voltage and charge are related like this. So the voltage across the capacitance at any given time is the charge across the capacitance divided by C. Okay, so, and since you're going from high to low voltage, it's negative QT by C. That's the time-dependent charge. And then you're going with the current, so you're going from high to low voltage minus IR. Okay, so let me write it. Let me write the time dependence more explicitly. So here's the EMF of the battery minus the charge divided by the capacitance, and minus I R equal to 0. But I and Q are related. All right, so we've done this before, but here's a very important lesson. The behavior of this system is given by this, the evolution of this system, the dynamical behavior of this system is given by this differential equation. And this is the mathematical model. Okay, so here's the mathematical model describing the behavior of the system. Okay. And we came up, how did we come up with this equation? How did we go from here to there? From here to there. You used a physical principle, and the physical principle in this case was Kirchhoff's rule. Okay. So, I mean, you'll do this as chemical engineers, mechanical engineers, and stuff like that. You'll have a system. You can set it up in a lab and study the system, or set up a mathematical model. Okay. So so here's the general principle you'll follow. You'll be interested in understanding the behavior of a system. Okay. So you can use some kind of principle and come up with a mathematical model. And then study this instead and make sure that the system behaves like that. Why do you do that? That's easier. You don't get your hands dirty. And what if your mathematical model is not accurately describing the behavior of your system? That means your model was an approximate model, it wasn't as good. Okay? So you refine your principle. Okay? All right, so this is all right, so let's erase all of this. Okay, so here was your system. You close the switch, and at t equal to 0, you close the switch, and for t greater than 0, you wanted to know the behavior of the system. Here was the mathematical differential equation that described the behavior of the system. Okay, and then you go take a differential equation class and learn how to solve these equations. Okay. So that's the general idea. Okay, you'll be interested, and this just where all does this apply? This idea. It applies everywhere. You can have economic systems. You can have biological systems. Okay, in biological systems, you can have prey and predator population that oscillate. If you have too many predators, what will happen to the prey population? They'll go down, and the feedback will make that predators will go down. So coupled equations will be hard to solve and all that kind of stuff. You know. So you can have any system, set up a model, and solve that model. The model is more than likely a differential equation. Okay? So you learn various techniques for solving differential equations. Okay? Yeah. So here is the solution to this differential equation. So the charge on this capacitor is building like so. CE. C is the capacitance, and this turns out to be the maximum charge, 1 minus e to the power of minus t over RC. RC is called the time constant of the circuit. Okay, that has units of time. That's the range, that's the time scale on which things change. So if t equal to RC, that is 1. E to the power of minus 1 is 1 over e is 0.35, roughly 0.35. So after one time constant, you have built up 65% of the charge. Okay. So that's what the time constant tells you. This is the maximum charge. Okay, at t equal to infinity, this term goes to 0, and charge, that's the maximum charge. So Q max, 1 minus e to the power minus t over tau. Okay. So here's how the charge builds. See, Q divided by Q max. There's how the charge builds. So if the time constant is small, the capacitor is charging fast. As you increase the time constant, the capacitor charges slower and slower. Okay, again, the time constant is RC. So if you increase R, you can charge the capacitor slower. Okay. All right, and the current is just dq by dt, and the current in the circuit is dying exponentially. Okay, it's charging exponentially, and the current is dying exponentially. Okay, so as the capacitor charges, the current goes to 0. Okay, so this is the basic RC circuit, and again, like I said, you'll see it in many applications. Okay, again, we learned a very important lesson here. Here's a system. You were interested in the behavior of this system. You came up with a mathematical model, which was a differential equation that described the behavior of this system, and you came up with a solution. Okay, so now you know exactly how the capacitor charges. Okay, and now you can do fun stuff with it. Okay, so let's see. One of the fun stuff you can do is, all right, here the battery will charge the capacitor. Now that you've charged the capacitor, remember in your flash camera, the capacitor was charging while that light was blinking orange. Okay, once the capacitor is charged, now the light is blinking green, and you're ready to take a flash picture. Okay, and when you click your camera, that's what happened. The capacitor discharged through the light bulb. Okay, this is how a heart defibrillator works. You charge the capacitor, and this is somebody's heart. Let's say this is somebody's heart that is fibrillating. That is, it is beating chaotically, and that had better be corrected very soon. And you pass a large current through the heart, and then it resets, starts beating regularly again. Okay. So this basic circuit shows up in places. Okay. So now what this okay, so in the last few slides we studied this part of the circuit. Now we're going to study this part of the circuit. We've charged the capacitor, and when you discharge it through a load, how does it discharge is the question. Okay, so that's the second part of this. Okay. So now you have a charged capacitor, and you're going to discharge it through this load. Okay, again, you close the circuit, and you're interested in the behavior of this system. How are you going to study this system? Well, you can set up a lab, buy expensive equipment, make hundreds of measurements and study, or be smart about it, set up a mathematical model and study. So that's what, since you guys are all differential equation experts, that's what we're going to do. All right. All right, so you use a physical principle to come up with an equation. And what is the physical principle you're going to use? Yeah, there you go. Okay, so we'll use Kirchhoff's loop rule. You have a circuit with a closed loop. The sum of the voltages across elements should be 0. There are only 2 elements. Okay, so so in this you're going around like that. Okay, so when you go from, you're going to higher to low voltage, minus Q over C, and then you're going minus Q over C, and then plus IR, because you're going against the current, plus IR equal to 0. Okay, when the capacitor is discharging, the charge is decreasing. So dq by dt, what is happening to dq by dt? What is this? Is this positive or negative? The charge is decreasing, and dq by dt is negative. So this is less than 0. Okay, so current current in the circuit is negative dq by dt. Okay? And that's what we've written. Current is negative dq by dt. All right, so the behavior of this discharging capacitor through the resistor is given by this equation. Okay? Again, you have a system, and the mathematical model describing the system is a differential equation. Okay? All right, and then you learn to solve it. Again, like I said, you are experts at doing this. There is the solution. Yep. So you see the capacitor discharges exponentially. That was the initial charge in the capacitor at t equal to 0. That was the initial charge. And again, that's the time constant. Tau is the time constant. The time constant is the characteristic time over which things change in that circuit. Okay. So if the time constant is a millisecond, all things change over the span of milliseconds. If you wait 10 seconds, everything is already done and over with. Okay? So if the time constant for this circuit is 1 millisecond, this guy will be discharged completely in 3 to 4 milliseconds. Okay? So that's what that means. All right, so now we'll do a few applications, okay, using this simple RC circuit. Okay, so let's say if somebody's heart is not beating regularly. Okay, so essentially their electrical system is messed up. Okay, so the beating happens like so. First, the right atrium compresses, it compresses, pumps blood here. Then this guy compresses, sends blood to the lungs. The blood flows back to the left atrium, which compresses, which sends the blood here, and then this compresses and sends the blood to the body. So it had better, all of that had better work in sequence. If stuff starts beating randomly, then you're all messed up. And you won't have much time. Anyway, so if this is a regular problem, you can have a pacemaker which will ensure that sequence of beating. Yeah. And so the pacemaker, I guess, probably sends an electrical signal there to get that sequence started. Okay. So now you know exactly how to do it. Okay, so here's a regular EKG. What you do is, so here's that circuit we just saw. It's drawn slightly differently, but it's doing the same purpose. Okay, so when the switch is open, what is happening is current is flowing through here, it's flowing through your heart, and it's charging the capacitor. Okay. You're charging the capacitor, and now, so the charge on the capacitor is built. And then when you close the switch, the capacitor discharges through your heart. It sends a current spike through your heart, starting the heartbeat here. Okay, starting the compression, or the compression of the right atrium. Okay. How often do you do this? You do once a second, essentially. Okay, so you have to fire this once a second. Okay, so your time constant of this circuit has to be, a tenth of a second or whatever. You want to charge the capacitor within a tenth of a second, and then every second fire the capacitor. Yeah. All right, so the time constant is a tenth of a second. You're firing it every second. Now, what if this guy wants to go for a run?
Faster?
I'm sorry?
It discharges faster?
Yeah, so you have to have a variable resistor. You got to have some kind of feedback, right? So you got to solve that as an engineer. All right, here's another fun problem. All right, so here's an electric eel. This is all under the sea. And here's a fish that is food. What you do is you pass a large current and the fish dies and then you can eat it. Well, here's the problem. This current is flowing through you as well. So you got to kill him without you dying. How do you do that? All right, so half of you guys did the experiment yesterday, and you should know. All right, so what you do is you have a, I'm going to, okay, so here's the eel, there's the current, and what you do is you get a whole bunch of parallel connections. So if this is 1 amp current flowing, and if you have 100 connections, how many amps are flowing through each element? A 100th of an amp. That's how you survive it. Okay? But the poor fish is not smart enough to do that, so the fish gets 1 amp through a region and the fish dies. Okay. Do you guys understand that? So that's how the eel solved this problem. Okay, so by the way, in most cells, the potential difference is 70 millivolts. Okay, that is, this is negative 70 millivolts, and that's 0 volts. Okay, so the outside or the difference, potential difference is 70 millivolts for most animal cells. The eels have specialized cells, and the potential difference is 150 millivolts. So those are the batteries. The batteries of an electric eel are electroplaques, each with an EMF of 150 millivolts and a resistance of internal resistance of 0.25 ohms. Okay, and so there's 750 of those in each array, and there's 140 rows of those. Okay, so the total voltage across this is, you're just adding the voltage, 150 millivolts, 150, and so all that adds up to there's 5,000 of those connected, 5,000 of those batteries, and the total voltage adds up to 750 volts. So this is seawater, and the resistance, total resistance is, along with the fish, is about 800 ohms. So the current that is flowing through is about 1 amp. So the eel can send a 1 amp current through this fish. That's plenty good enough to kill the fish. I think you can kill humans too with that. Yeah. Okay, so the current through the fish is 1 amp, but the current through each row is only 6 milliamps. Okay, and that's how the eel survives. All right, I guess I've been lecturing for a long time. Did you want to hear any of this stuff? Okay, we'll pause.